Okay, so in this section 1.7, we're going to be working with really two different ideas. One, we're going to be dealing with functions that we can write from data, okay, using our regression in the calculator. Okay. Now keep in mind there are ways to write those regression equations by hand, but we are not going to do them by hand. Okay. Some of them are quite tedious. Even the linear one is tedious. So we're going to just use the calculator to write the equations for us at this point, and our job is to interpret and use. Okay. But the other part of our work today is going to be dealing with functions that come from formulas. Okay, we have lots of formulas, especially in geometry. Okay, when we dealt with shapes, there was lots of formulas for area and volume and surface area and so on. Okay, so what we're going to look at is a few examples here of some problems that are going to come from formulas that we know. And in this case, what it boils down to is we have a square. It's got side x inches. It's cut off from a corner of an 8 by 15 piece of cardboard, and the sides are folded up to form an open top box. Okay, so let's visualize what that's going to look like. Okay, there's a nice picture here on the slide. If we have this rectangular piece of cardboard and we cut squares out of the corners, okay, then those four things are going to be flaps, and if we flap them up, put tape on it, we'd have ourselves a box. True? All right. Now, think of why we would want to know about anything like this. If you look at this box right here, okay, that might be a box that that a shirt gets put in from the mall that you buy. True? Now, if you're the person that's selling the shirt, okay, what would be the best case scenario for the box that you use? Okay, ultimately, the more material you use, the more it's going to cost. So you want the cost ultimately to be a minimum for you. True? So that means if you could make if you could take a piece of cardboard, whatever piece you're given, in this case, let's say we have 15 by 8 pieces, okay, would there be a way that we could get the maximum volume out of that box? Okay, wouldn't that be good? Okay, would there be a certain way that we could cut this so that it would give us a maximum volume? Because if we cut these too small, then it would be kind of a wider box, but it would be quite shallow, wouldn't it? Okay, or if we cut too far, it would have, the bottom part would not be very big, but it would be kind of tall. True? But if we did somewhere in the middle of that, okay, we might find that there's an actual way to find a maximum volume here. Okay, because ultimately, if we have that piece of material to work with, we'd want to get the most out of it. Okay, otherwise, we're going to end up not using our money very wisely. Okay. So the question that we're going to ultimately pose here is, in the end, how big should the cutout squares be in order to produce the maximum volume? Fair enough? So the general strategy here is going to be dictated by what these questions are. This is kind of what we're going to do for each of these problems. We're going to try to write an equation, okay, for whatever we're trying to maximize or minimize. Keep in mind, this could be a minimum problem also. Okay, so we're trying to write a formula for what we're trying to maximize or minimize as a function of x. Okay, and we're going to also consider the domain. Okay, and then we're going to look at the graph, and we're going to see, is there some maximum volume here? Okay, so let's go each step at a time. The first issue here is writing a volume formula, and in our case, volume here equals LWH because this is going to create a prism. So we know that the volume of a prism from geometry and from your blue note packet, something that you don't have to have memorized, it's right in your packet, that length times width times height is going to be the volume of any prism. So the question is, if we can do it in terms of x, that would be great, because right now there's no way I can graph this. I don't have L, W, and H in my calculator. There's nothing to graph. And we need to write an equation that has one variable. Okay? And what it boils down to is if this box, if we cut x into each of these corners, okay, if we cut an x by x square out, then ultimately in this direction, okay, this is all 8, but if these two are x, then what is this leftover piece right here? Okay, it was 8, and we subtracted x and subtracted x to get this part. Okay, so therefore, wouldn't it be 8 minus 2x? Okay. And keep in mind that right there that I just marked, that's one of the sides of the box. True? Same thing here. This ultimately started out at 15, but we cut out x and we cut out x. So what's this new part right here that's going to be the other side of the box? It's going to be 15 minus 2x. So there's our two dimensions for the length and width, if you will. And then finally, if we flip up these flaps, if you will, this part right here, keep in mind that's x also. So if I flip that up, wouldn't the height of it here, wouldn't the height be x? It would go x into the air, wouldn't it? Okay, and hence, what's the other dimension? X. So with that said, there's our length, width, and height. Okay, or height, width, and length, I should say. But it doesn't really matter what order I put them in here. But bottom line is I just created myself a volume equation. True? And remember, what I want to find is what is the maximum volume. Okay? And if we were to multiply all that out, we would recognize that we have a cubic function. And we know some cubic functions look like this. So at some point, could there be a maximum? Sure. Okay. So let's check it out. First thing we want to look at is, first of all, how about the domain? Okay. Because we know that the domain of any cubic function is negative infinity to infinity. But in the case of x here, we're talking about an actual cut we're going to make. Do any of the negatives make sense? So we don't want to use anything greater than 0. And even 0 itself, would it make sense not to cut the box at all? Okay. So really 0 wouldn't make sense to be part of the domain here either, would it? And the other question is, how far can we cut? Think about this. If this is 8 and we're cutting in from both sides, how far could we cut so that we wouldn't have a box anymore if we cut too far? Yeah, wouldn't 4 be the maximum here that we could cut on x? Okay, we can cut 4 here and 4 here on the 15 side and not do any damage. But if we cut 4 into both directions and met in the middle, what would happen to our piece of cardboard? We would have just lopped that whole thing right off, wouldn't we? And then we wouldn't have a box anymore. There'd be nothing to flap up. Okay. So, with that said, okay, our domain here then would be 0 to 4. They have the 0 included on this. I would say that the 0 probably shouldn't be included, like I said, because the 0, and really even the 4, that's not going to give us the box either. It's going to make our piece of cardboard worthless. So I would suggest that we should write 0 to 4 here. Okay, recognizing that 4 and 0 are not going to give us valid answers here. Okay. All right, now, next key issue is, can we draw a picture of this and find the maximum? Because like I said, it's a cubic function, so we know there should be a maximum. So I'm going to go ahead and put this in the calculator. I'm going to turn off my stat plot again. So if I put that equation in, you can multiply this out if you want to, but really, is there any need to do that? I mean, if I were you, I'd just leave it in this factored form. That way it's less work. So if we go 8 minus 2x, 15 minus 2x, and we look at a window here. In this case, if I did my standard window, if I did zoom 6, you can start with that if you want to. You may or may not see something that's useful. And you can see that you don't see really anything useful there. We don't see a maximum or minimum. We're just seeing a little bit of it going through by the origin. So we're going to want to make that a little bit bigger here. So in my window, I'm going to change my x min to 0 because I don't need to see any negatives here. I'll stick with 10 here because it looked like there was some stuff going on between 0 and 10. But then my y min and y max, I'm going to make my y max up to 100 once and see if I can actually see something useful. Okay. And I do see something useful, and that's good. Okay. And we can see it does have the shape of that cubic function. We could make the window bigger and see the maximum or the minimum point down here also, but do we really need the minimum in this case? All right, so at this point, we need to find that point right there because that's where the volume is going to be a maximum, okay, on this interval. And again, remember, it continues over here, higher and higher, but this part over here is not within that 0 to 4 domain, is it? So we don't care about what's going on over here. All we care about is that point right there. So if we use the maximum command, move that cursor back up to the top there. Go left, right, and middle. And we can see our maximum point is 1.667 and 90.741. That would be the maximum point. We can interpret the 1.6 repeating as 1 2/3 also. Okay. This is not a recognizable decimal, so we just round that one. Okay. And remember, in answering the question here, okay, two things. If the maximum point is this, then what does that tell us? That the maximum volume is the y coordinate here. Remember, this is a volume equation. So the maximum volume we could get out of this box would be 90.74 inches cubed. Okay, and that would occur if we cut 1 2/3 inches into the box for each of those corners. Okay. Questions so far? One of the things that makes pre-calc different from calculus is that this problem in calculus, we would actually be able to find the exact value for that, right, instead of having to take these decimal approximations. Because think about it, if I'm going to use this kind of information to do something important, like send a rocket to the moon, right, are just decimal approximations going to be cool if you're the pilot? Not for me. I want the exact answers. True? So we'll be able to find that exact answer at some point when you take calculus, okay, but that's beyond what we're going to do in this class. So right now, we can still answer the question, but we have to settle for a decimal answer for it and not the exact. Okay? Okay, questions so far? Okay, I want to look at one more here with you, and then we're going to have an opportunity to just practice some of these. Okay, all the problems are a little bit different today. All of them involve using formulas, okay, for this part. Okay, you got a bunch of geometry formulas that are right in your book, okay, that you're going to be kind of manipulating here. But if you look at this one, it says grain is leaking through a hole in a storage bin at a constant rate of 5 cubic inches per minute. The grain forms a cone-shaped pile on the ground. As it grows, the height of the cone is always remains equal to the radius. And it says if the cone is 1 foot tall right now, how tall will it be in an hour? Okay. All right. So we need an equation here, and we need to first of all recognize what shape we're dealing with, and that's a cone. Okay. Now, we also need to recognize in the cubic inches per minute is kind of a giveaway. This is what we need to look for here in the units in this kind of problem. If I say cubic inches per minute, inches cubed is a volume, okay, and obviously minutes is a time. Okay. So they've given us a rate of the change in volume. So knowing that, okay, what we want to do is write down a volume equation for this shape. So if you either have it memorized or you look it up in your notes, the volume formula for a cone is 1/3 pi r squared h. Okay. Now, if we're going to write this equation, okay, and we know that, like I said, currently the height of the cone always remains equal to the radius. Okay, and that's kind of a giveaway for these two variables, because at this point we have two variables, so it would be nice to only have one, wouldn't it? Okay. But by saying the height equal to the radius, that means that h is equal to r. That means that one of these I could substitute for the other. True? And again, I'm interested ultimately in how tall this thing is. True? So if I were to write that equation in h instead of in r and h, I could replace the h, and I could replace the r with h, and wouldn't I have then h cubed? Because I'd have h squared times h here. Okay, so I'm just taking that h, plugging it in for r, and now I have the equation that just has two variables in it, which is good, because now I could graph it if need be. Okay, and I could use it to answer some questions here. So with that equation, okay, let's take a look at what we did here. So again, here's our volume of cone. When the height is 12, okay, that's what they said. The height is it's 1 foot. Okay, they want to know inches here. Well, because we need inches here because remember the units were inches cubed. So that means that our volume, if we put a 12 in there, it's 576 pi inches cubed. Okay, 1 hour later, okay, the volume will have grown by 60 minutes times 5 inches cubed per minute. Okay, so in other words, the volume will get that big now. So that would be the new volume after the time frame. They said an hour later. Okay. All right, and so that means the total volume will be this. Okay. It was 576 pi, and now it's 576 pi plus 300. Okay. And remember, this is where that other equation comes in that we did, because remember, all we care about is the height. True? So if we have our volume, our new volume, if you will, and we know the equation that it's equal to, then this is just going to be a matter of solving for h. Okay. So that's what they did here. They solved for h, okay, and end up with a 12.63 inches is the final result. Okay. So solving this, remember, we would multiply by 3 to get rid of the 1/3, divide by pi, okay, and then ultimately to get h by itself, it's cubed, so we have to take the cube root of both sides. And if we take the cube root of both sides, okay, we get our 12.63 inches. Okay. Questions so far? All right, so again, those are just a couple of examples. In your work on your assignment today, okay, you're going to be given some problems that are similar to that using shapes and being able to write equations from the shapes. and hopefully coming up with some correct answers.